Understanding the notation in the definition of a limit. Well, the first thing we probably have to do is understand what the precise definition of a limit is. So let's take a look. So here we have a linear function, and let's say that I want to predict the height of a function at, I don't know, say a comma L. Well, let x marks the spot here. And we want to estimate what the height of the function is going to be at this value. But let's say that our function is actually this, I don't know, let's call it a unicorn at the coordinate x comma f of x, or x comma y. Now, since the limit predicts where the height of the function is going to be, that doesn't necessarily mean that the height of the function is going to be there, because as we can see here, this unicorn is a free roaming unicorn, meaning they can go wherever it wants. It's not restricted by anything, which makes it very challenging to predict. Fortunately for us, we have been talking about limits before, and we know that we try to get as close to the x value as we possibly can to help us demonstrate what the y value could be. So, I can put in these kind of little barriers here that kind of fence my unicorn in. It's like, oh no, I can't leave these fences, ah! So we've kind of trapped the unicorn left to right, but we can still go up as high and down as low as we want. So I can then put matching fences on the top and the bottom. And now by putting these fences in here, I have restricted where the unicorn can go. It's kind of now fenced in and boxed in, which makes it easier to predict where the actual height is going to be. Now, since the unicorn can move all the way over to the left to this fence, we're going to call this fence a possible x. And since the unicorn can move all the way over to this side, this is also a possible x value, and same thing with the lower fence and the upper fence. Those are both possible f of x values. Now, fortunately, we did restrict our unicorn, but still, the unicorn doesn't have to be on the x marks the spot. It can be anywhere. So while this is helpful, it's not, super helpful. But what we can do is we can move our fences closer to the value that we want, just like the limit as x approaches a. So if we move them in closer, the unicorn is now still free roaming, but he's kind of restricted to where he can go. He has far less area for him to roam in. So as we continue to move these fences in as x gets closer to a and f of x gets closer to L, as our actual height gets closer to our predicted height, we're going to continue to limit the space that our wild unicorn can frolic in. And if we keep limiting this space, we're eventually going to get to the point where the unicorn has no place to go but to be on that x. So as we shrink the distances vertically and horizontally, we shrink it so much that a unicorn has to be on the x marks the spot. Or we shrink it so much that the intended height will give us an accurate prediction of where the function's going to be. So, what is our goal in this whole process? Well, our goal in this whole process, as we said, is that we want to make the distance between x and a as small as possible. And in making the distance between x and a as small as possible, we will also make the distance between f of x and L as small as possible. Now let's just quickly remember here that we said a refers to the actual value, and a refers to as the intended value. And same thing, f of x is the actual, whereas L is the intended. So again, that is the goal. We want to shrink the distance between x and a as small as possible as to trap the unicorn. And by shrinking the x values, we are then going to shrink the distance between the f of x and the L value, again, fencing our unicorn in. So, if we really want to get the unicorn on that x, don't we just want to make this 0? So, if we want to make the distance between x and a as small as possible, can't we just make the distance between x of a be 0? And that is a great question. Let's talk about that. So if the distance from 0, or if the distance was 0, that would mean that the intended height is the actual height, which you might think, that's great news. But let's remember that the limit is basically a prediction. It tells us nothing about the actual height. So that means that the distance between x and a can never be 0 because we can't tell from just the limit alone whether the prediction is true. So no, unfortunately, we can't make the distance 0 because, again, we don't know what the actual height is. We just want our prediction to be as accurate as possible. Alright, so then what about making the distance between f of x and L be 0? Well, again, for the same reason, no, we can't make the distances between those two be 0 because we don't know enough about the actual height. We're just predicting it. We're getting as close and as close and as close as we can without actually knowing. It's kind of like walking up to the side of the Grand Canyon. You can get as close to the edge as you want, but as long as you don't fall in, you're good. Okay, well, if we can't make the distance 0, now what do we do? Well, we can come in here and we can define some terms. So let's call the distance between x and a the absolute value of x minus a. And if we can think back to when we learned about absolute values, remember we said absolute values help us define distance. So that's what we're doing here. And then we can take the distance between L and f of x and have that be the absolute value of f of x minus L. Now, since we probably want these distances to be as small as possible, we should probably define some, super small values. For example, we're going to let this symbol, well, we're not going to let it, it does. This symbol is the Greek letter for delta, but we're going to let delta equal some infinitesimally small number. Basically, the smallest number we can possibly think of, that's delta. And then we'll do that again. We'll take some infinitesimally small number, and we'll set that equal to the Greek letter epsilon. Alright, so now that we have these items defined, we can now get to work. So, in order for our limit, aka our prediction, to be as accurate and precise as possible, we said our goal is to get f of x as close to L as possible. Which means we want the distance between them to be the smallest possible value it can be. Well, fortunately for us, we have already defined epsilon as being some infinitesimally small number, the smallest possible value. So, what if we just made the distance between L and f of x less than the smallest number possible? Because if something's smaller than the smallest number possible, it's got to be incredibly small. So therefore, what if we take the absolute value of f of x minus L and make it be less than an infinitesimally small number? This would make the distance as small as possible without it being 0. Because remember, we said this distance can't be 0. So therefore, we're just going to make it as small as possible by making it smaller than the smallest number ever. We can use the same idea for x and a. We can set the distance between x and a to be less than our infinitesimally small number, delta. This would also make the distance as small as possible, and again without it being equal to 0. So, what does this all mean? Well, it means that as long as the distance between f of x and L is as small as possible, whenever the distance between x and a is as small as possible, then the limit as x approaches a of f of x is going to equal L. We are going to have an accurate and precise prediction. Yay! Woo! Time to celebrate! Oh yeah! Alright, that's enough celebrating. Time to get to work. Alright, so here is the mathematically precise definition of a limit. And as you can see, it's much more wordier than our definition, but it says basically the same thing. So we're going to assume that f of x exists for all x in some open interval containing a, except possibly at a, because again, the limit is a prediction, not an actual value. Then we say the limit of f of x as x approaches a is L, which is written as the limit as x approaches a of f of x equals L, if for any number epsilon greater than 0, infinitesimally small number, there is a corresponding delta greater than 0, infinitely small number, such that the distance between f of x and L is less than this epsilon whenever the distance between x and a is greater than 0, but also less than this infinitesimally small number delta. So again, this is a much more accurate mathematical definition, but what we went through says generally the same thing. Alright, so let's take a look at our first example. So we're told that if the absolute value of x minus 1 is greater than 0 but less than delta, then the absolute value of 4x plus 5 minus 9 is less than epsilon. What is the limit we are trying to prove? Alright, so the main thing we're being asked here is, what is the limit we're trying to prove? Which means we need to write a limit. And we know that our limit formula, I guess we can say, is the limit as x approaches a of f of x is equal to L. Which means we're going to need to identify certain pieces of our limit in the question we're given. So let's go ahead and break this down. We know that with delta, we are linked with x minus a. And we know with epsilon, we are linked with f of x minus L. So based on what we're given, we can see that a is going to be 1, f of x is going to be 4x plus 5, and L is going to be 9. So therefore, we can just substitute these into our limit. So we're going to end up with the limit as x approaches 1 of 4x plus 5 is equal to 9. And that is the limit we are trying to prove using the precise definition of a limit. Let's take a look at another example. So here, similar situation, we're being told that the absolute value of x plus 1 is greater than 0 and less than delta. Then the absolute value of 5x plus 2 plus 3 is less than epsilon. What is the limit we're trying to prove? So we'll take a similar strategy as last time. Again, we're trying to fill in the pieces of our limit. And we know that delta corresponds with x minus a, and epsilon corresponds with f of x minus L. Well, the problem with this particular example is that we don't have x minus a number, we have x plus a number. However, we know that plus can be rewritten as subtraction, and we can rewrite this as x minus a negative 1. And by doing that, we can see that a is going to be negative 1, f of x is going to be 5x plus 2, and then L is going to be 3. And now we can substitute those values in. We're going to get the limit as x approaches negative 1 of 5x plus 2 is equal to 3. And that is the limit we're trying to prove with the given information. Alright, so next up, we want to determine values of delta from graphs. So here, we're letting the limit as x approaches 3 of f of x equals 5. For each value of epsilon greater than 0, determine the value of delta given that epsilon is equal to 1. So let's talk about this for a second. We know that delta corresponds to our x values, and that epsilon corresponds to our y values. So basically, we're given our y values, and what we're trying to do is we're trying to solve for x. So this is very similar to what we usually do in math when we solve equations. We start with a function y, and we solve it for x. And we're going to do a similar thing here. We can see that our epsilon is equal to 1, or that somehow y is going to equal to 1. But okay, before we can do that, let's pull apart our limit here. So we can see that our a value is going to be 3, and that our L value is going to be 5. And as you'll notice on the graph, that is where our unicorn is. And we can see that the L value is at 5, and the A value is at 3. Now, we said that the distance between L and f of x is epsilon. So, that means to go and figure out what our fencing is going to be to kind of restrict where this unicorn goes, we're going to have to add epsilon to our L value. So we have 5, so 5 plus 1 is going to give us 6. So that means our upper limit is going to be here, and this is L plus epsilon, or 5 plus 6. And then we can go one down from L, so this would be L minus epsilon, and that'll be at 4. And as you can see here, we have now created our upper and lower fences. Now we just need to figure out what the left and the right fences are. And the question is, well, how do we do that? Well, to figure out the x values of the left and right fence, we just need to figure out where these where these up and down fences intersect the function. And our lower fence intersects the function here, so that's where our fence is going to go. And then the upper fence intersects the function here, and that is where our other fence is going to go. Now again, these values, they represent our x values. And delta is the distance from A to x. So to figure out what delta is, we just need to count how far it takes to get, in this case, from 3 to 5 and from 3 to 1. And we can see here that delta is going to be a value of 2. So when epsilon is equal to 1, delta in this particular case would be 2. Now, honestly speaking here, we can see that our unicorn has a lot of room to roam. So 1 is an extremely large number in this case, and 2 is an even bigger number. When we would actually be evaluating real limits with these things, epsilon would be so itty-bitty you couldn't even imagine how small it would be, making delta that small too. We're just using these super large values so that you can actually get the picture of what's going on. So let's take a look at another example. Same example, same function, limit as x approaches 3 of f of x equals 5. But this time we want to find delta when epsilon is 1/2. So again, we know that our a value is going to be at 3, and our L value is going to be at 5. Unicorn's already there. We know that we have to go up from 5 by 1/2 to get our upper fence, and down from 5 to get our lower fence. So that means we're going to be at 5.5 and 4.5. So this is L plus epsilon and L minus epsilon. And then we just need to figure out where these two fences intersect our function. They intersect our function right here and right here. And those will be the x values for which we put our left and right fences. And as we can see, we've restricted the unicorn a little bit more here. And then we can use these fences to figure out what our delta value is going to be. And we can see that from 3 to 4 it's going to be a value of 1. From 3 to 2 it's going to be a value of 1. So therefore, when epsilon is equal to 1/2 in this particular limit, delta would be equal to 1. And this information would kind of allow us to prove that particular limit. It wouldn't really, because again, 1/2 and 1 are super large numbers. But again, we're choosing those on purpose. Alright, so I just want to compare the two fencings that we talked about. The first fencing was when epsilon is equal to 1. And we had this large area for our unicorn to frolic and gallop in. But then as you notice, as we shrunk our epsilon by only 1/2, we significantly decrease the distance for which the unicorn can roam. And this goes back to our precise definition. The smaller epsilon is, the smaller delta is, which means the more accurate or precise our limit is. Again, that's the goal, to create the smallest possible epsilons and deltas. Alright, our next example is a little bit different. So suppose that we are trying to show that the limit as x approaches 4 of f of x equals L. Which one of the following deltas would work when epsilon is equal to 1? And so we can look at our graph here, and this graph isn't really drawn correctly, but I pulled it right from Newton so we can go over it. So as we can see, we do have the L value right here. And we do have our epsilon equals 1, which means we're going to have our L plus epsilon fence right here, and we're going to have our L minus epsilon fence right here. And now, fortunately, I've already drawn our fences for us, because we have the intersection point here and the intersection point here, which allows us to find our left and our right fences. All right, so now we just need to figure out what delta values would work. And we're trying to figure out which delta values are going to fit in between our two fences. So let's take a look at our first delta value. Our first delta value is 1, 5. So that means, 1, 5. Whew. Our first delta value is 0.5. So if we go 0.5 away from our A value in the left direction, and we go 0.5 away from the right, we are well within our acceptable fence area. So this particular delta value would work. All right, next up, let's make delta equal to 1. So if we go 1 up from our A value and 1 down from our A value, that still puts us right in between those fences. So, oh, wrong one. So that one is good. All right, next up, let's check 2. So from my A value, if I go up 2 to 6 and down 2 to 4, I'm still well within the fence area. So 2 would work as a delta value. All right, next up, let's take a look at 3. And what color can I use? I can use orange here. So 3 means we're going to be going up to 7, and we're going to be going down to 1. But with this side, our orange goes past the fencing, which means 3 will not work. It is outside of our fenced-in area, would not give us a precise definition. And then we can look at 4, but if 3 didn't work, 4 is obviously not going to work. And 4 doesn't work because we crossed the boundaries on both sides, so that one is out. So therefore, for this particular question, an acceptable delta value that would give us the precision that we need is 0.5, 1, and 2. All right, on our final example here, the following graph shows an example of epsilon and the response value of delta for the limit of the function, the limit as x approaches a, of f of x equals L. And we're being asked to identify the epsilon, the delta, and the correct concluding statement for these particular values of epsilon and delta. Now, we're given the graph and we're given the choices, and this problem, the way it's worded, makes this sound so difficult, when really it's pretty easy. First thing we need to do is we need to identify our epsilon and our delta value. Remember, epsilon is up and down, delta is left and right. So that means that epsilon is going to be 1/3 because that's the distance up and down from L. And delta is the distance away from A, so therefore our delta is going to equal 3. So with just that fact alone, we can go ahead and cancel out answers. So we know that epsilon can't be, or epsilon has to be 1/3, so that means it can't be 3 for either of those. And let's see, then our choices that are left has epsilon with 1/3 and delta have 3 for both of those. Okay, so now we just have to play the more advanced elimination game. So let's remember that epsilon has to be greater than f of x minus L, and delta has to be greater than x minus A. So I just need to pair those up. So, again, we know that epsilon is 1/3, so we know that the absolute value of f of x minus L has to be less than 1/3, and come on, Wi-Fi, catch up. And we know that since delta has to be greater than the absolute value of x minus A, and that's a horrible looking delta, I need to go in and fix that guy. I tried to fix it and I just made it worse. And that's horrible too. Come on. Alright, not great but better. And then we can see here that the absolute value of x minus A then has to be less than 3. And the only answer choice with x minus A being less than 3 and f of x minus L being less than 1/3 is our first choice.